All right, back to our worksheet problem. Here we've got this strange bent wrench, and we're trying to loosen a bolt, and we want to calculate the torque in the configuration if the bolt's at 0.2, 0.3, and we're pushing with 10 newtons in the plus y direction at xy coordinates 0.5, 0.4. And the idea is there to calculate the torque. One way to calculate it is the magnitude of the force times the moment arm, and to visualize the moment arm, we always draw the line that contains the force vector and say to that line, what is that shortest perpendicular distance to the rotation axis? So in this case, the magnitude of the force is 10 newtons, and our perpendicular could be visualized as this distance. It's 0.3 meters. So it's 3 newton meters of torque. I didn't define which way was positive here, but we're just concerned with the magnitude of the torque. Similarly, I want to, in this case, 3 newton meters of torque. In this second case, B, I want to ask if I push on the end of this wrench inward along the arm direction toward the left, how big of a force do I have to apply in order to still have 3 newton meters of torque? So again, I'm going to use the relationship torque equals F times moment arm. And in this case, I know the torque I want is 3 newton meters. The moment arm is, well, again, you draw the line that contains the force vector, and you say to that line, what is that perpendicular distance to the rotation axis? And in this case, the moment arm is only 0.1 meters. So that means F times 0.1 meters, I want to be 3 newton meters, and therefore, when I divide by 0.1, I get 30. I'm sorry, this is mistakenly written here. It shouldn't be 30 newton meters. F is 30 newtons. The units for torque, because they're units of force times a distance, are newton meters in SI units. So this shouldn't have a meter in it, but just 30 newtons in that case. Because the moment arm is smaller, you know this isn't a very effective way to use a wrench, so you have to push harder if you want to turn it with the same kind of oomph as you are in this direction. Okay, C, let's put the picture up here. You have to see the picture to know what C is talking about. In this same configuration, but again, we're pushing now not on the end of the wrench, but on the elbow, that right angle point right there, and we're pushing it at an angle of 30 degrees with respect to the horizontal. If we push with a 10 Newton force, what magnitude force are we applying? And in this case, I could use F perpendicular times R. I could use R perpendicular times F, but it's kind of hard to imagine. If I draw the line that contains this force vector, it's hard to imagine what that perpendicular distance would be. We could still figure it out, but it's simpler in this case to use the perpendicular component of the force times the entire R. In other words, if this is the force, perpendicular component means perpendicular to the R vector, which points from the rotation axis to the point at which you're applying the force. So this is the R direction. The component of F that's perpendicular would be the component along this direction. And that has magnitude 10 times cosine of 30. And the R in this case is the length of that R vector is 0.1 meters. So if I multiply those together, I get 0.866 Newton meters of torque in this case. All right, good practice examples. Now let's go on to what seems like a more complicated problem, and it is on the surface more complicated, but we can reduce it down to the same kind of thing. We've been assuming in our definition of torque that there's only one place where a force is being applied to an object. Or maybe if you've got an object with a fixed rotation axis, you might have a couple of forces. Each one generates a different torque. Here's something different. Here's a wall of a building. We've got a hinge right here so that this big piece of metal can rotate about the hinge. And we know if there's nothing holding it up, if we let that thing go, it's going to flop down and hit the wall, right? So gravity is trying to start it rotating in this direction. Gravity is the force that's going to try to rotate this rigid body about this fixed axis and make it rotate in the direction sort of downward from where it is. Whether that's positive or negative, we'll make a definition shortly. But the confusing thing is there's not just one place where the force is being applied. Gravity is being applied all along here. In other words, it's pulling down on the tip, and it's pulling down on this part, and it's pulling down on this part close to there. So just for definiteness, I'm going to define the direction that it's going to tend to rotate with gravity to be the positive rotation direction around the hinge in that direction. And if I divide up this piece, I'm going to consider the gravitational force on each of these little bits of mass. So I'll assume the one out on the end has mass m1, then the next one m2 and m3, and so on. And in that case, gravity is applying a force at this location here to m1 that has magnitude m1g. It's also pulling on m2 with force magnitude m2g, and so on. It's pulling on all of these with different magnitude forces. And if I want to calculate the the torque associated with each one of those, I need to multiply each force times its moment arm. So this force m1g goes with a big moment arm out here. I would call that x1 because it's associated with m1. So m1, that force m1g has a moment arm x1. That's the distance of the applied force perpendicular to it down to the rotation axis. m2g has a moment arm x2, and so on. And so if I want to get the total torque due to all of these gravitational forces, in other words, the torque due to gravity, I might call that the net torque on this if gravity is the only force acting on it, is the torque due to the gravitational force on the first bit plus the torque due to the gravitational force on the second bit. We got to add all those up for all the little bits and pieces of it. That looks complicated, but let's persevere and we'll be able to simplify it. There's a common factor of g, which I can factor out of all the terms, and I'm left with just what remains in parentheses there. And what we're going to do is multiply what will be the numerator by m, and then we're also going to divide by m. If you multiply by m and divide by m, you don't change this ratio right here, so that's all we've done there, where we're going to let capital M be the entire mass of this whole thing. In other words, it's the sum of all those little masses, or just the total mass of the thing that's rotating. So that's what capital M means. And then we're going to make a definition. Everything except the capital M times g that's out in front, everything that's in parentheses divided by capital M, we're going to define that to be the x-coordinate of the center of mass, and I'm assuming here the x-axis is horizontal when I say that. So if I rewrite that in terms of it, it just means that the net torque due to all these little gravitational forces distributed over the whole thing is the total weight of the object, total mass times g, times one moment arm, which is the center of mass x-coordinate, and that center of mass x-coordinate we're imagining is at the location of this little black and white wheel here. So its x-coordinate is this distance. Okay, so the upshot is, if with this definition of x-coordinate of center of mass, if you need to calculate the gravitational torque on an extended object, you can pretend that the entire weight force is only being exerted at the location of the center of mass, and we use the corresponding moment arm only for the center of mass. So even though I have a whole lot of different forces being applied due to gravities on lots of little bits of mass, we can pretend that the entire gravitational force is located at the center of mass for the purpose of calculating the gravitational torque. Okay? Let's take a break and we'll come back.